Today we're going to be talking about local linearization, which is tangent lines and tangent planes. The tangent line or the tangent plane is going to be the best linear approximation to a function near a point, as all those elements. Tangent to a function near a point, because tangent lines are going to be different at different points on a curve, or tangent planes are going to be different at different points on a surface. So let's start off with an old problem and upgrade it to a new problem. So here's an old version of a problem. Find the equation of a line tangent to a curve at a given point. We can also ask this question by asking, what's the best linear approximation of the function 9 minus x squared near x equals 2? So that would be an alternate way of asking for you to do the same thing. So what's the best linear approximation? Here's an alternate version of that same question. Find the equation of the tangent line. Tangent line is the best linear approximation near a point. The important thing is here we have a point, and that's what we're going to make our approximation. Once that point changes, we need to reevaluate what direction the function was going. So we know this is just going to be a line containing the point 2 and f of 2. That's going to be the point. And it's going to have a slope of f prime of 2. So our equation will look like y equals, start off at f of 2 and add the derivative at 2 times x minus 2. This is just a point slope equation of a line. This is a line containing the point 2 comma f of 2 with slope f prime of 2. So here's a line that contains the points containing the point 2 and f of 2. We just evaluate the function to find the y coordinate of the point, and it has slope f prime at 2. That's what the derivative is for. We've known that since the very beginning of calculus. So it's all pretty straightforward to calculate. If x is equal to 2, we'd have to find f of 2. F of 2 is going to be 9 minus 2 squared. So that's going to be 5. F prime of x is minus 2x. So f prime of 2 is negative 2 times 2, or negative 4. Assuming I did my arithmetic correctly. This is a very dangerous assumption to make. So our equation is going to be y equals 5 minus 4 times x minus 2. I tend to prefer lines in point slope form. This is a question centered at 2, 5. This is a question about what's going on when x is equal to 2. We can multiply all this out into slope intercept form. But we don't really care about what's going on when x is equal to 0. That's really far away from 2. But it's not incorrect to rewrite this equation. It would not be incorrect to rewrite this equation by multiplying everything out. So I have a minus 4x, and then 5 minus 4 times, the minus 4 times minus 2 is going to be plus 8, and 5 and 8 is like 13 or something. This is telling us that the slope, the y-intercept of this line is 0, 13. Who cares what's going on when x is equal to 0? We're trying to approximate the function here too. I guess the point I'm trying to make is that we need to point slope type equations. I suppose we could also write this equation in standard form and say 4x plus y is equal to 13. Usually we follow up this question by asking to approximate the function 9 minus x squared, which does seem kind of ridiculous because it's a simple function. Let's pretend that f of x is some wacky function at this point. So if we wanted to evaluate or approximate the function near 2, I could just plug, say, 2.1 into the equation of the line. And we would see that 0.1 show up in the x minus 2. Let's suppose we wanted to approximate this. Use the linear approximation. We could use the tangent line to approximate f of 2.1. Also, we could just calculate what f of 2.1 is. 21 squared is not that far off of what we would need. We would subtract that from 9. Life would be much simpler. We know what function we're dealing with. But that's not the point of the exercise. What we want to do is take the 2.1 and plug it into the tangent line. And regardless of what this value is, we can see the structure of what's going on. The last time we checked in with the function, when x is equal to 2, the function gave us a value of 5. If we're going to do a linear approximation, we're just going to take the delta x 0.1, because the 2.1 is 0.1 off of where we calculated our tangent line, and we'll multiply that by 4. The actual value is not important. Seeing how what this calculation is telling us, that's what's important. Start at 5 and decrease by 4, 0.1 times. 5 minus 0.4 is 4.6. That's like the least important part. What we care about is this 0.1, that's some small change in x. And this negative 4 times 0.1 is how much y changes. So 0.1 is a change in x. And the negative 4 times 0.1 is the change in y. question? The point of the problem was not 4.6. It was understanding how to read these changes in X, producing a change in Y. Is everybody okay? Of course, it's tangent lines. Tangent lines are a thing from top one, and we're experts in top one. That was like a whole year ago that we were learning about this stuff. One thing I do want to take the opportunity to point out is, notice when I look at the standard equation of this line, 4x plus y is equal to 13. Remember what we learned about the cross product? How we could describe a plane by saying it's all the stuff that's perpendicular to this one normal vector. And the coefficients of that plane in the standard form are going to be the components of that normal vector. Let's think about the line equals negative 4x plus 13. This line has a slope of negative 4, so we'll drop down 4 and go to the right 1. Or you think you're going up 4 and left 1. A lot of times we say down 4 and over 1. Over is not a direction. Left and right, those are directions. But that's neither here nor there. If we take a graph where the slope is negative 4, we'll go down 4 and right 1. Let's imagine a line now. One of the things that I advertise this class on is that top 3 is just top 1 and top 2 smashed together with functions of more than one variable. We have to do our differential stuff, our integral stuff, all in one semester. But that's okay, because we remember all that stuff, and we're just adding functions of more than one variable to it. But that does mean we need to be consistent. And so when we read the equation y equals negative 4x plus 13, that negative 4 indicates this line. It goes down 4 and right 1. When we write this line in standard form, I get 4, 1 as coefficient. Let's pick a point on this line and do 4 in the x direction and 1 in the y direction. So if I go 4 in the x direction and 1 in the y direction, say the 4i plus 1j note that that vector is perpendicular to the line with the slope of negative 4. Everything is nice and consistent. When we write our linear equations in standard form, the coefficients of x and y are going to be normal to the curve. If I have an x, a y, and a z, those coefficients are going to tell us the vector that is normal to the plane. If I have an x, a y, a z, and whatever comes after z, if I have 4, those coefficients will give us a vector that is normal to the three-dimensional solid in R4. All this stuff needs to be consistent. And so it's nice to see when it is. Questions? So notice that the slope of that line is -4. So the perpendicular slope should be 1/4, positive 1/4, and we can see that slope, positive 1/4, that the vector 4i plus 1j. 4 being the run, 1 being the rise. That vector is normal to the line. Any questions? We want to do the same calculation within the same context where, the same calculations in a different context. The same calculations, but with a function of 2 variables. So we're going to be creating a surface. And we can find the equation of the line tangent to the surface at a given point. So upgrade our line to a plane. That's going to be because we are upgrading our function from a curve to a surface. We are going to construct this line, this plane, the same way we constructed the line. We'll pick a starting point. That'll be the function evaluated at that point. And then we'll have the derivative in the x direction multiplied by the change in the x, and the derivative in the y direction multiplied by the change in y. So our equation is going to be the function evaluated at 2, -1. We have a function of 2 variables, so f prime doesn't mean anything anymore. We replace prime with x and say the derivative in the x direction evaluated at 2, -1 times the delta x plus the change in the y direction evaluated at 2, -1 times the change in y. Got to say y plus 1 because it's y minus a negative. This fits the same stuff that we had before. The x minus 2, that's going to be a delta x. So the x minus 2, that's a delta x. And the fx at 2, 1, that's delta z over delta x. If I multiply those two together, that'll give me the change in z. Similarly, the y plus 1, that's going to mark some change in y. And so fy at 2, 1 times y plus 1 will tell us how much z changes. So this f of 2, 1, 2, -1, that's like our starting point. Then we add how much change in the x direction, and we add some amount of change in the y direction. Let's make some calculations. So I need f of 2, 1. That's going to give my starting point. Sorry, 2, negative 1. So that's going to be 9 minus 2 squared minus a negative 1 squared. So 9 minus 4 is 5, minus 1 is 4. I need to take both of my derivatives. And as you can see, I took it easy on myself and made them both the same because lazy. So we take the derivative at xy, and that's going to be 9 minus, oops, let me get rid of the 9. Derivative of 9 minus x squared minus 2 minus y squared is going to be negative 2x. Because 9 is constant with respect to x and negative y squared is constant with respect to x. And then we just plug in our points. So fx at 2, negative 1 is negative 2 times 2, negative 4. And then we do the same thing for fy. Fy at xy is negative 2y. Fy at 2, negative 1 is negative 2 times negative 1 or positive 2. Now I got all the pieces I need put together into my plane. I'm going to start off at 4 and decrease by 4 whenever x changes from 2. We're going to increase by 2 whenever y changes from negative 1. This is going to be our best linear approximation to this surface above the point in the beginning. Just like before, we could multiply all this out and find out what the z-intercept of this plane is. So I could multiply everything by the negative 4, multiply through by the 2, and just figure out what our constant is. And I could say that z is equal to negative 4x plus 2y, and then just have some constant. And this will tell me what's going on above 0, 0. We don't really care about that because we're talking about things near the point 2, negative 1, not at the origin. But sometimes we ask for equations in strange forms. So I got 4 minus 8 is negative 4 plus 2 is negative 2. So here's that plane in kind of a slope intercept form. We can also put this in standard form like we did before. And I could say this is 4x minus 2y plus z equals negative 2. Way back in algebra, when we taught you the standard form, we didn't have things like vectors normal to a surface. We didn't have perpendicular lines. But we didn't make a big deal about this standard form and what it told you, because that predates our understanding of how vectors work. But now that we have vector technology and vector training, we can recognize the coefficients of this plane, the equation of this plane in its standard form will tell us a vector perpendicular to the surface at a point. So the vector That 4, -2, 1 is normal to the surface at point 2, -1, 4 on the surface. Just like before, we could use the equation of the tangent plane to approximate the function at a point near 2, -1. So we could use the tangent plane to approximate the value of the function near the point 2, -1. I'll put 2.1 and -1.1. So my delta x is going to be 0.1, and my delta y is going to be -0.1. I'll try to make them stand out a little bit more. Now my delta y is going to be -1.2. The idea is that we'll plug these into our equation, and it would make more sense to plug them into the point slope version of the equation rather than slope intercept. Because the point that the slope that's we're centering on the point slope equation, the point that's featured there is 2, -1. So let's use that, since 2.1 and -1.2 is close to 2, -1. So the 0.1, there's our delta x. Here's our delta x. And the -0.2 is our delta y. And the 4 times 0.1 is our change in z. And the 2 times the -0.2 is our delta z. So you got 2 different delta z's, one in the x direction, one in the y direction. So 4 minus the 0.4 is 3.6. 3.6 minus another 0.4 is 3.2. The usual question that comes up with this kind of problem is, why don't we just plug 2.1 and -1.2 into our original function? If I ask you to evaluate this function at those points, I wouldn't want an approximation. I want to use the original function. The original function is just a polynomial. Polynomials are super easy to work with. Why would we plug it into that? That's not the point. The point is not approximating a function that we already know, especially with the amount of computing power we come equipped with these days. Think about all the computing power that we have just right in our pockets. We just say, hey, Wolfram Alpha, tell me some stuff about this function. And it'll evaluate it for us. That isn't the point. There could be situations where all we know what's going on is a location and a direction. So all we get to do is approximate with a linear function. We don't know what the actual function looks like. We just know where things are now and where they're headed. With that, we can make a linear approximation. Any questions? It's really weird to envision calculus in this way. Because in calculus, I always hand you a function and ask you stuff about the function. But the real game is take some derivative information and figure out what the function is. And what's especially entertaining about that game is when we don't have any way of actually figuring out what the original function is. All we get to do is create an approximation. So this is an important thing, not to be able to write out the calculations, but understand how things are built and understand how they're related to each other. Because in the classroom, you're always handed a function. But in an actual analysis situation, you might not have any idea what the functions look like. We're going to have to look at a bunch of data, see what the values are, and see how those values are changing to speculate about the form of the function so that we can run tests and figure out what the function might look like. Any questions? Comments? Deep thoughts? Reminds me of a mechanic I once had and an unreliable car that I used to drive around in. And how if I pulled that car into the mechanic, he would just listen to it for a second and tell me what's wrong. He would just listen to it and say, it sounds like your water pump is about to go. Because you've got to take all this information and figure out what the function is. In class, when you're learning about that, I would pull the car up and say, this car's water pump is broken. Figure out what it sounds like and then fix it. That's me handing you the function and you doing the analysis. But we've got to be ready to play the game in reverse. Some customers got to be able to pull up and you listen to the car, you gather some data about what's going on, then you figure out what the function is. You figure out what the problem is. That's kind of a big part of what goes on in math. It's not about answering questions. It's about figuring out which questions to ask. No questions? What really bothers me when people talk about math and say, well, there's always a right answer. Yet when you're handed a question, what if we need to go out and figure out what the question is? How's everybody okay? Here's another one of my bottom lines for what school is about. At the time that you graduate, your schooling is all done. It doesn't matter if your bachelor's degree, your master's degree, your doctorate degree. At the time that you graduate, if you don't have more questions than when you started, you kind of wasted your time. I think a lot of times we go into school and we figure out this is where I'm going to get my questions answered. And that's kind of the point. You come in, you get some questions answered, but the answers to those questions need to lead to more questions. If they don't, you're just watching TV. You're not becoming educated. You're just watching stuff happen. You know what I mean? When you graduate, you better have more questions than when you start. That's the point. How's everybody okay? The main thing I wanted to do today is say, hey, remember tangent lines? And y'all be like, yes. I go, tangent planes down. And you're like, oh, all right, seems pretty easy. Well, it only seems pretty easy and straightforward because it is, because we've already done it. Questions? Comments? Snide remarks? All right, That is actually all I wanted to talk about today. Get thee unto the homework and start working the problems in chapter 14. Tomorrow we'll start talking about gradients. We got direct derivatives in the x direction, derivatives in the y direction. What about derivatives in some other random direction? That's the thing for tomorrow. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day. Thanks for playing.